All right, so today's lesson, angles and angle measures. But if you look at our target or our goal for today, we're just going to convert degrees to radians and back. So we are going to finally learn about that other mode in your calculator known as a radian. Why you always had to change it to degrees or else you get the wrong answer. But that's going to be like the back half of the class. The first part, we're going to learn more about just how we can view angles in a more specific, more mathematical sense. And this is going to kind of lead up to the next several learning targets where we're going to learn about something called the unit circle. Ooh, and I saw some eyes flashing over to that dry erase board I have on the side wall in my classroom that looks like a bullseye or something. And we are going to be getting to that later on this week. And essentially the whole purpose of this in the next probably 3 learning targets is we're ultimately trying to find a way that we can very easily just kind of know a bunch of some of the more common trig functions or the trig ratios without having to rely on a calculator or something like that. So if someone were to say, hey, Wojcik, what is the sine of 30 degrees? I can just say, oh, that's 0.5. And so you're going to get to that point where you can just rattle it right off the top of your head. Or if someone says, hey, what's the tangent of 5 pi over 4 radians? You'd be like, oh, that's a positive 1. And that's our goal, so that when you're doing calculations, it can be nice and quick and really easily. And it's going to take several lessons, several days, several learning targets, but that's kind of where we're going. Yes, sir? No, it's only 3 targets. Yeah, it's this Friday. Do you want me to put that on there too? Sorry. There. Is that better? I'll make it look nicer for you later. Yes, we do have your next test this Friday, but remember, it's short. It's probably only going to take you half an hour at most. It's only on 3 learning targets. They're pretty small. And angles. All right, so we're talking about angles, and we want to come up with a formal mathematical definition of an angle. Not just oh, that angle in this triangle is 14 degrees or whatever, but how can we structure it? And so we're going to look at all angles now. We're going to consider them in what's called standard position. And standard position is on a coordinate plane. Think of your x-axis and your y-axis. And we're going to put angles right on that coordinate plane. And we're going to measure starting from the positive x-axis. So if you think about it, on the x-axis, to the right is positive, to the left is negative. So to the positive x-axis, meaning to the right in the coordinate plane, we're going to say that, hey, this is 0 degrees. That's our starting point for an angle, to represent an angle. And then any angle will be based off of that direction. And angles are measured counterclockwise. That means if I went up this way, then I would say, hey, this right here is a 50 degree angle, something like that. You're measuring it as you go counterclockwise, like moving up. But if we went in the other direction, maybe down to here. So if I measured from there to there, that arc that I've drawn kind of below the x-axis, that's actually going to be in the negative direction. And we would measure an angle still in degrees, but we'd give it a negative number. So all the way straight down would be 90 degrees. This is a little less than that. So this might be a negative 80 degree angle. So we're measuring that angle, if we had a protractor, we'd measure it from the x-axis as being the 0 point, the positive x-axis. And if you go upwards, or if you're continuing rotating around that coordinate plane, that'd be considered a positive angle, counterclockwise. But if you start from the positive x-axis and move downwards, towards that negative 80, it's going to be a negative angle, a negative measure in the clockwise direction. So if you're spinning clockwise, it's a negative angle. If you're going counterclockwise, it's a positive angle. And each of those 4 different quadrants on the coordinate plane, you know how you have 2 lines, it splits the coordinate plane up into 4 different groupings. Those are called quadrants. Each quadrant would be exactly 90 degrees, because isn't this right there, that's a right angle? Those 2 axes are perpendicular, they'd meet at a right angle or at 90 degrees. So hey, if each of those are 90 degrees, how many degrees is it all the way around that entire coordinate plane? 360. Oh my gosh, fantastic. He can do multiplication and yet can't wear a mask on his nose. All right, so in this slide, everybody, all I want you to do, I've got a coordinate plane there, and I've got the first quadrant labeled for you. So quadrant 1 is actually always in the upper right, because this is where it's positive, positive. Like if I had a coordinate here, it's a positive x value and a positive y value. Like that's the main part of the coordinate plane we typically work with, positive x values and positive y values. That's why it's the first one. I want you to go ahead and just reach back in your memory to previous years of mathematics. And can you label the other 3 quadrants for me, 2, 3, and 4? And also while you're at it, at each of the different axes, each of those 4 axes, I want you to write how many degrees each of those would represent, knowing that each quadrant is 90 degrees. So if that's 0 on the positive x-axis, our starting point, how many degrees would it be up there and on the left and down at the bottom? Did you already finish? Man. Do the quadrants? Now do the angles. So think about it. How many degrees each of those would be? And I want you to give me just the positive measure of each of them. So measure it counterclockwise. What? How many degrees are each of those?
I'm confused. Wait, no, I get it.
Liam, how many degrees is that? 90. Okay, so this is 90 degrees. It's a positive 90 degrees because we're going counterclockwise. You probably all labeled the quadrants first. Hey, what's the quadrant here in the upper left? What number is this? That's 2, right? This is quadrant 2. Let me use red. Quadrant 2. And then down in the bottom left, that's quadrant 3. Excellent, excellent. And then what's left over with this is quadrant 4. And so if you ever were wondering, probably whenever you learn about the quadrants, why do they go counterclockwise? That seems backwards. You know, it's not really that intuitive. You think normally, you know, things go clockwise. Like clocks go clockwise. That's why it's called that. And that'd be really convenient because most things that we see spinning would be clock hands, and they all spin in a certain direction. But why do these go backwards? Why is quadrant 2 to the left and not down below? And the reason being is because this is how we measure angles in that positive direction, moving upwards, going counterclockwise up to 90 degrees. Down here, if we continue that pattern, how many degrees would you be here straight out to the left on the negative x-axis? Yeah, that's right. You're just adding like another 90 degrees. And so if up there was 90, go down another 90 degrees, and this would bring you to 180 degrees. Down at the negative y-axis, right down there, if you added another 90 degrees, what number would you get to? Woo! Someone's good with mathematics. 270 degrees. And if you added 90 one more time and you went back to 0, what number would you actually get up to? 360. Okay, so like one full spin around the circle is 360 degrees. You've maybe heard of this if you ever watch any like snowboarding or skateboarding competitions when they do like a full rotation in the air. That's called a 360 because they spun 360 degrees. If they do 2 complete spins, that would be a 720 because they did 360 times 2 basically would be 720 degrees and various multiples of that. I can do a 540 on my inline skates, in case you're wondering. I'm kind of cool like that. That's right, that's 1.5 spins. That was back in the day, before I became an old man. Now I could probably still do it. I could do it like standing still probably, from right here. Just jump up in the air and do a 540. Maybe later. I want to hurt myself. Yeah. But I could also just do it in like my shoes probably. Should we all try it? Do you all want to try doing a 540? Jumping up and spinning? Yeah, I bet you would.
So I can't get it back?
Yeah, fine.
You can do a backflip. So it's a 360 again. I can do a backflip.
Ready? You're only going to get this once. So one full spin and then another half a spin, right? So I should be facing that board. Those of you at home, this is amazing. Just in case. I got this.
Are they all trying it? Or?
I don't know. Thank you. Thank you. Thank you. That was 1.5, right?
Yeah.
1.5 spin. So 360 plus another 180. That was for mathematics purposes, everybody, in case anyone saw or was asking, like walking by. You could tell them your teacher was demonstrating principles of geometry or trigonometry. I can't. All right, so here we go. For those of you who missed it, whenever you see me again, you can ask me to, and I will replicate the 540 for you. All right, so an angle has its vertex at the origin and its initial side along the positive axis. So we're going to be looking at these angles on the coordinate plane, and an angle is made up of basically two rays, as they're called. They have an endpoint and an arrow. They go on forever. Basically, you're thinking of two lines. There's one, there's another, and the angle is basically the measure of rotation in between those two. So I do need two lines. On this coordinate plane, once we formalize these angles in standard position, we actually have names for them. First off, the vertex, which means like the corner of the angle, that is always going to be at the origin, at 0, 0, the intersection of your x and y axes. And the initial side, well, the word initial kind of means the start or the beginning. Like your initials start your name, don't they? Aren't your initials like the beginning of each word in your name? But initially means what are you, like the beginning, things like that. So the initial side is the starting side. The initial side of these are always, always, always going to be on the positive x-axis. This is kind of locked in on that positive x-axis, the axis off to the right. That's always our starting point because that's 0 degrees. So that initial side never changes. The other side of the angle, though, that one does change. That's called the terminal side. And terminal means the end. Just like that one robot guy, the Terminator, right? He terminates people. He ends them. Wow. So terminal means to end, or you may have heard like an airport terminal. That's the end of your flight at the airport from the starting destination to an ending destination. That's the terminal. And so that just means the end. Now the terminal side is the part of your angle that's actually going to rotate. Think of it like being attached with like a spinner right in the middle. You know, there's something holding in place. And this part right here can kind of spin around and around and around that origin and kind of keep on looping all around. And that's going to be your measure of your angle, or how many degrees of rotation from that initial side. So this basically was rotated from this initial side up there. Remember, we're going to measure counterclockwise because that's the positive angle of how many degrees of rotation it passed through. So this would be an angle somewhere between 90 degrees and 180 degrees, right? Because it's right in between that positive y-axis and that negative x-axis. We know that that's going to be, I don't know, maybe like 140 degrees, something like that. And so you look from the initial side to the terminal side. Everyone okay with this so far? It's just showing you how we put angles on the coordinate plane. And what I want you to do now is think about their location on that coordinate plane and figure out what the actual angle for like the blue angle would be. So for example, X here, it does say 70 degrees, but this clearly isn't a 70 degree angle because I'm talking from here all the way over to there. Well, that's definitely going to be more than 70 degrees. So how do you figure out how many degrees it is? Well, from this positive y-axis, we're moving an additional 70. So what you need to do is think about, well, how much is it from the initial side up to that positive y-axis, and then go an additional 70 on top of that, and that'll be your total angle. So go ahead and try to think about each one of these three, angle X, angle Y, and angle Z, what the actual degrees of rotation are that blue angle went through. I want the positive number of degrees from the initial side to the terminal side. How many degrees of rotation do each of those three different angles represent? Yeah, good. Nice. Okay. Doing some color coding?
Yes.
Awesome. Can you think about these other two also? How many they would be? Do you remember what's straight down?
270 plus
Yeah.
40.
So if it's going in this direction, would you add the 40 or subtract the 40? So what would you get then?
I'm confused.
How much is it going straight up? How many degrees is it?
180,
Well, look right here.
90.
It's 90. So if straight up there is 90 and you go 70 more, what number do you get to?
Okay.
Can you try to figure out these other two? Think about like what straight down is from here, and if that's 40 away, what would it actually represent? Oh my. What? Let's see if he, oh, no, he's not even on the right slide. All right, so for this one right here, here's what we would think about. We start from the initial side, which is on that positive x-axis, and I'm rotating counterclockwise to get to the terminal side. Now, from here to there, we know that that's one complete quadrant, which would be 90 degrees. From the 90-degree mark, though, I'm going to go an additional 70 degrees. Now, that's still counterclockwise, so it's going to be another positive rotation. So we basically just add these two numbers together. So we're just going to add up the 90 plus the 70 for a grand total of 160 degrees. Who else got 160? Yes. Awesome, awesome. Going to this middle one, angle Y, we can do something similar. We can think of if I started from that initial side and I started rotating in this direction, I went a 90 degrees plus another 90 degrees plus this amount right here. But I don't know how much that is. But I do know that from here down to there is 40. So what I could do is think about, well, this entire quadrant I know is another 90 degrees. But it's 40 degrees less than that. So if I subtracted that 40, I get 50. So I do know that this amount of rotation here is another 50 degrees. And so there, I've got my three counterclockwise measurements. I went up 90 degrees, then another 90 degrees, down to the negative x-axis, and then from there, from like right here, I went an additional 50 degrees. And so we can just add up those three numbers, basically. 90 plus 90 plus 50. Well, 90 and 90 is 180. 180 plus 50 is 230 degrees. Another way that you could have answered this one that might actually be a bit easier is if you simply recognize, look at this measure right here. You can say, okay, well that 40 degrees is being measured from this negative y-axis. Do you remember how many degrees it is straight down? That's a 270. So you can think, okay, well if we start from 270, and I go clockwise, which is backwards, so you want to think like negative, right? Because clockwise is a negative number. So if I'm at 270, but I go backwards 40 degrees, or I subtract 40, what number would we get to? That's right. So it's like we're subtracting 240 and we get 230. So you can do it that way also. And you're still going to get the same number if you recognize that. How many of you did have 230 for angle Y for this middle one? All right, good. Now the crazy like hypnosis one. And that spiral just means that we're doing more than one rotation. We're doing multiples. Kind of like me at the skate park when I'm shredding it. That's a skater term. You might not know what it means. Thanks. So we're going to start right from the initial side. And here's how we're going to think about this. If I'm going all the way around, one complete rotation, how many degrees would that be? Yeah, one complete, spin around would be 360 degrees. But I didn't stop there. I went another complete rotation around. So how many degrees did I just go again? Yeah, another 360, right? Which would add up to 720. So I'm going to add another 360. So now I'm up to 720 degrees. But I'm still not done yet. I didn't get to the that terminal side quite yet. But if I go this, well, I didn't go a complete rotation. I went half of a rotation. How many degrees is that? That's a 180, right? Half of a spin is 180. So I'm going to add a 180. That gives you a total of 900 degrees. Equals 900. So 900, that would be 2.5 complete rotations, as made famous by Tony Hawk, professional skateboarder. I don't actually know him in person, but I've played a lot of his video games, so that counts, right? So that would be a 900 degree angle. Anyone get the 900? I saw a number of you had that. Just double checking that you're following along. Awesome. Yes, sir. Yeah.
I hate spiders.
Oh my gosh. Anyways, that last one with like the multiple spinning, that actually has a special name. Whenever you go beyond the 360 and you get to these additional angles. So when multiple angles in that center position, if they have the same terminal side, since we're spinning around multiple times, we could have multiple angles ending at the same place. And if they do that, they're considered to be co-terminal. The word co just means like together. And then terminal, obviously, that means they end that way. So if that terminal side ends up pointing like basically in the same direction. And here's what I mean with this example down here. If I look at this 50-degree angle on the left, let me trace this with my the purple marker here. And so I've got that 50-degree angle. But if I took this angle and I moved it, so I'm not changing the measure, it's still 50 degrees, but watch this. As I move it over here to the right, to this 410-degree angle, see how it matches up like perfectly? It's the exact same thing. It's the same angle, essentially. It just has one, I just took out one full spin, or I took out a 360. Those two angles differ by exactly 360 degrees because that's one complete rotation around the circle here. And so there's a unique property about these coterminal angles. Since they essentially open up the same amount, like if that was an alligator mouth, they'd both open up the same. There's something kind of cool that happens. Can you all get your calculator out real quick for me? Thank you. I want you to take your calculators. And let's do some basic trig. Let's do the, sine. I want you to take the sine of both of these angles. Take the sine of 50, see what you get, and then right? What'd you notice, everybody? They are exactly the same. Doesn't it seem weird? The sine of 410, 410, that's a huge number. That's gigantic, but it's still the exact same ratio. Because if I were to like make a triangle, it doesn't, we wouldn't care about the extra rotations around. I would just be drawing this line like from there to there, or from there to there. So for the 50 or the 410, it doesn't know what the difference is between extra rotations. It just cares about like this end result, like the net displacement from the initial side to the terminal side. It doesn't care about how many times it's spun around. So these are coterminal angles. They're going to have the exact same values. And that's true if you do other trig function values too, like cosine of 50 and the cosine of 410 is also the same value. Not the same as the sine, but it's its own value. So 0.6427, blah, blah, blah. Hey, what do you think would happen if we added another 360 to 410? What do you get? What is 410 plus 360? 770? Let's see what the cosine of 770 is. 0.64278? Again, it's the same thing. And the other cool thing is we can go backwards also. So here I'm at 50. What if I rotated in the negative direction? If we took 50 minus 360, we'd get negative 310. So watch this. The cosine of negative 310 equals, and there it is, everyone, the exact same decimal, the same ratio. That's why these are considered coterminal angles. Now, the nice thing about this, like why we need to understand them, is because essentially there are only 360 possible values, no matter how many times you spin around. So if I keep on adding 360 over and over and over again, I'm still going to have the exact same like small angle, like that ending angle. And so, as I mentioned, one of the goals of learning this in these next few lessons is to be able to identify trig ratios very quickly. Like I want you to be able to calculate the sine of 45, or just know it off the top of your head. Well, if you know that one, then you also know the sine of 405, and you know the sine of 715. Like if you keep on adding multiples of 360, they're all going to be the exact same values. You don't need to memorize an infinite number of possible angles. There's only these 360s. So if you have a negative angle, or if you have an angle that's bigger than 360, you can just add or subtract 360 multiple times, and you're going to get another angle, a coterminal angle, whose properties are identical to that original one. So instead of working with 410, we can instead just work with 50, which I'd rather work with 50 than a 410 or a 770 or whatever those other bigger and bigger angles are. And so what I want you to do right now is practice identifying coterminal angles. So I got three angles here for you, J, K, and L. And all I want you to do is to identify two additional coterminal angles. Now, there are actually an infinite number of coterminal angles for each of these, because I could keep on adding 360 over and over and over again. But I just want you to give me one positive coterminal angle and one negative coterminal angle. So 15 degrees is angle J. How would you find another coterminal angle to 15 degrees? Since you're just going to like add a 360 or subtract a 360 to get down to a negative angle. So for each of these, I want you to give me two angles, one positive and one negative, but they all need to be coterminal for each of those three different angle measures. So you should be coming up with a total of 6 different numbers for me. Awesome, but is that negative? Ooh, what do we do? So you subtracted, you didn't get to a negative number? How can I get down to a negative number? What do I have to do? Exactly. Yeah, good. Is this a negative number? All right, looks like we're all getting the general idea. look at that. Figured it out. This is your unit. All right, just walking around the room, it looked like most of you knew what was going on. If I had 15 degrees to find another coterminal angle, we're just going to add like one complete spin around the circle. We're just going to add another 360 degrees. That would give us a positive 375 degrees. If I want to get a negative coterminal angle, I'm just going to keep on subtracting 360 until I get to the negative numbers. So 15 minus 360 gives us negative 345 degrees. Did any of you have those exact two values? Awesome. Are these the only possible coterminal angles, though? No, there's an infinite number of them, right? I could keep on adding 360 over and over, or I could keep on subtracting 360 over and over again. All right, angle K. If I added 360 to a negative 200, we'd get 160 degrees, a positive 160. Whereas if I took that negative 200 and I subtracted 360 degrees, we'd get a coterminal angle of negative 560 degrees. Did anybody else have those exact two values? Okay. If you had different ones, that's okay too. Those aren't the only answers, right? There's an infinite number of possibilities. Now this last one, angle L, add a little trick to it. First off, the positive coterminal angle, most of you had 1,360 by adding 360. But what you need to think about is to get a negative coterminal angle, a lot of you subtracted 360 and you got 740, which is coterminal, but is 640 a negative number? Well, it's not. So what do? Well, I just need to subtract another 360. So from 640, if I subtracted 360, I get 280, right? That's another coterminal angle to 1,000 degrees. Is that number negative?
No.
Not yet. We need to subtract 360 one more time to get down into the negative numbers. When you do, we should get a negative 80 degrees. Anybody else get the negative 80? Awesome. And so just know that it won't always be just subtracting automatically gets you a negative number. You might have to subtract multiple times. Or if you were given a pretty negative number, you'd have to add 360 multiple times to get up into the positive values. All right, so just so you know, there's all these coterminal angles that all have the same trig values, essentially, if you evaluate them. Just like we tried out with the calculator with the 50 and the 410. They have the same sine, cosine. Concept in terms of these angles and standard position is something called a reference angle. So every standard position angle, every one of those angles from like 0 to 360 has a much more useful angle called a reference angle. And what it's referring to is basically how far away that angle is from the x-axis. And so we always measure up from the x-axis. And there are two criteria for a reference angle. So you can have any possible angle, any number in the world, but the reference angle is going to be very specific. These are the two properties of it. First off, is your reference angle needs to be acute. Does anybody recall what acute means if you think back to geometry? An acute angle is just less than 90 degrees. Very good. Hey, look, it says it right there. Good job, class. The second thing is we're measuring this value from the x-axis. And so some of your reference angles are going to be compared to the positive x-axis. Others are going to be compared to the negative x-axis. And so look at this example right here. This standard angle is 140 degrees. I want the reference angle for 140 degrees. It needs to be acute, and it needs to be measured from the x-axis. Well, this is from the x-axis, right? It's measured from right there. That's the positive x-axis. But is 140 degrees an acute angle? It is not. It is an obtuse angle. I need the angle that's less than 90 degrees. And so instead of comparing this, seeing how far away it is from the positive x-axis, I'm going to take a look and see, hey, how far away is that same angle away from the negative x-axis? I'm just looking for what's the closest distance that that angle is, that terminal side is, from the x-axis. And so from here, if I'm at 140, and down here on the far left, like the negative x-axis is 180 degrees, we're really just taking a look to see, hey, how close is 140 to 180? And hopefully you can realize that 180 minus this 40 degrees, or minus 140, gives me this leftover of 40 degrees. So the reference angle would be 40 degrees, because that's an acute angle, and that's how far away that same terminal side is from the x-axis. Now, based on which quadrant you're in, you're going to measure this differently. So this right here, this is in quadrant 2. And so you basically subtract that angle from 180. If it were down here in quadrant 3, you would take 180 and you would subtract it from this angle. So you're seeing, hey, how far apart is it from here to here? What's that distance? And if your angle were in quadrant 4, we're just looking at this distance. You're just looking how far away is it from the x-axis. And you don't have any negative values. It's just the absolute value. It's just the positive version of how many degrees away is that angle from the x-axis. Now, again, why are we doing this? Why are we looking at these smaller reference angles instead of the bigger ones? Well, I have a surprise for you. Go ahead and grab out one of those fancy graphing calculators again. Whoops. Doesn't have to be graphing. Clear this out. And I've got two different angles here, right? 140 degrees and 40 degrees. Now, 40 degrees is the reference angle for 140. What I want you to do is find the cosine of both of those angles, and then I want you to calculate the sine of both of those angles. Okay, so I want you to do 4 calculations. Do the sine of both of these angles and then the cosine of both of them in your calculator. And compare those values. See how they might relate to one another. It's very exciting. Isn't that crazy? So what did you see? What did you realize, everybody? They're almost all the same. And the ones that are different, are they similar? Yeah, one's just positive and one's negative, but it's the same number, right? The same decimal. Let's take a look up at the board here. Sine of 40 and the sine of 140 are both the exact same ratio, 0.642787, blah, blah, blah. They're the exact same value. The cosine of 40 and the cosine of 140 is the same decimal, but just one of them is negative and one of them is positive. But it's still this 0.76604444. So we're going to learn more about why the sines are positive of these two and the cosines, one's positive, one's negative, later this week on Friday. But the key thing that I want you to realize is why do we care about reference angles? Is since they are so similar and they're almost the exact same number with just one being negative, is this also helps us kind of use smaller values. Whereas instead of working with 140, I can just work with 40 degrees and pretty much get all the same answers. So again, this is just a way to enable us to understand exact values of any single angle ever in the world, right? On these on the coordinate plane, these standard form angles. So if you wanted to figure out the sine of, say, 500 degrees, well, you'd say, well, this 500 is coterminal to 140. And so instead of knowing what the sine of 500 degrees is, you can say, oh, it's the same thing as the sine of 140 degrees. And then we know, wait, I don't need to worry about the sine of 140. I just need to know what the sine of 40 is, the reference angle, because the sine of 40 is going to be the same as the sine of 140. And so we took this angle, 500 degrees, and realized that, hey, the sine of that angle is the same as the sine of 40. it turns out that we can kind of condense every angle to be some number between just 0 and 90 degrees. And so all we really need to work on is if we can figure out what these exact values are for the angles in between 0 and 90, we can pretty much then apply that to any other angle beyond 360 or even less than 0, any single angle at all. We can all bring it back to just that basic quadrant 1 for those values. And what's even better than that is we only need to know basically 4 values in one quadrant. I'm only going to have you try to figure out or know 4 values in one quadrant. And those same numbers will apply for every other angle that we need to learn. And that's coming up later this week. Ooh, I'm so excited. Yeah. So let's practice identifying these reference angles. So I've got 3 angles here for you, angle X, Y, and Z. And they're the ones given to you in blue. And I want you to calculate the reference angle for each of these 3. So remember, all you're doing is trying to calculate how many degrees away from the x-axis that angle actually is. And it needs to be should be a positive number, and it should be an acute angle. So it should be a number less than 90 degrees. What is the reference angle for each of those? You're just kind of comparing how far away are each of those terminal sides from the x-axis. Just like this first one, you're just really trying to compare, hey, what's this little distance right there? How many degrees would that be? If that terminal side is at 170 degrees, what would be that little sliver at the bottom? Nice. Yes, good. This is your unit. Good. Oh my gosh. Did this back corner just become like Genius Town or something? That's kind of scary. Yes. Hey, that looks good. Yo. Hey, that one's right. Good job, Lucas. Yeah. Hey, good work. Yeah, those are good. So, like for this first one here, I'm going to compare it to, like, this is the x-axis. How many degrees is that there? To the straight out to the left is how many degrees? Yeah. If that's 180 degrees, and this line right now, this angle is at 170 degrees, how far apart are those two numbers? Just 10, correct. So this would be a reference angle of 10 degrees. For the middle angle, angle Y, I'm going to measure this from the negative x-axis again, which is 180 degrees. And I want to know, hey, how far apart is this 225 degrees from 180? So how far apart is 180 from 225, everybody? It's 45 degrees apart, which you can get just by subtracting those two numbers. So this has a reference angle of 45 degrees. Last, that one over on the far right, angle Z, since this terminal side is pointing more, like it's pointing to the right, I'm going to measure it from the positive x-axis this time, unlike those first two where I measured it from the negative x-axis. And if this angle is currently 295, I need to figure out, well, how far away is it from this positive x-axis? Now, if you remember, that positive x-axis is actually two values. It's a 0 and it's 360. And I can compare it to either one of those numbers. But if I compare it to 0, I know it's going to be 295, which is way too big. That's not an acute angle. So instead, we're going to compare this to 360 degrees. And so all we're trying to figure out is how far apart is 295 from 360. And if you just subtract those numbers from each other, you should get 65 degrees. How many of you had all three of those? I saw a good number. That was really good. Very impressive. Any questions on any of these reference angles? And so the nice thing with these reference angles is you'll notice that they're all going to be acute. So as long as we can figure out these basic trig functions, sine and cosine and tangent of, wow. Oh my gosh. Did you just do an acute joke? Oh my gosh. That's... Okay, moving on. Okay, so now we're done with the all those angle relationships and things like that and how to measure them and that kind of fun stuff with spinning around the coordinate plane. Now it's time to learn something really exciting. I know you've been waiting for this for a really long time. I bet that you were just thinking, man, why'd I got to change my calculator into degree mode? What is this radian thing that Wojcik tells me I need to change? Let me start off. This is just a little fun history lesson for you right now, so you can just chill, you can just relax. Let me draw a circle freehand. Oh, what? Did you see me? I don't want to. What do you mean there's no way? I could draw a really good circle. Pressure's on now.
Pretty solid, actually.
It's okay. Right, the little top there, but it's quite rotund. It's uniform. What's easy, smaller? I think that one's worse.
100% worse.
All right. Oh, that's, no, it's embarrassing. Yeah, you can use your full arm as a radius. So a circle is basically defined as an infinite number of points a set distance away from the center. What it means is if I've got a center point here, my circle, and I want you to connect or show me every single point that's, say, 5 inches away from this, well, there's a point there, there's a point there, there's a point there, and every one of these points are the exact same distance away from the middle of that circle. And if I were to plot every single point, there's actually an infinite number of them, these points would be so close together that it just looks like a line going all the way around, and that is what a circle is. That's its definition. It's the collection of points that are a set distance, called a radius, away from a center. And for some reason, that doesn't actually make sense. If you ever stop to think about it, why did someone decide that we should split a circle up into 360 different pieces and call each one of them a degree? Like, why would they use the number 360? Doesn't that seem like an odd choice of a number when so many things in our world are like base 10? Like, why not make it 100 degrees altogether? And then when you divide it up into fourths, each one would be like 25 degrees, like a quarter. You know, why not make each of these 25, 25, 25, 20? I mean, that would be a quarter of a circle. But instead, a quarter of a circle is 90 degrees. Why 90? Like, we're used to that because we grew up with it. But isn't that kind of a strange choice in numbers when everything else is like base 10 in our number system? You know, 10, 100, 1,000, and so forth. Or what if we made each quadrant like 100 degrees, and then the whole circle is 400? Something like that would be really nice. Numbers would work out a little bit better. But no, we have a circle that's broken up into 360 pieces. Like someone decided, let's just split this up, and let's slice this cake 360 times and call that our circle. Why 360? Any guesses? They like numbers. Why not 362? Actually, why not 365? It's not an even number. But why do you think thousands of years ago, some mathematician peoples decided, oh, let's break a circle up into 360 parts? What's 360 really close to? 365, which is the number of days in a year. So is it possible to hypothesize that maybe a couple thousand years ago, some bright math people were like, hey, every approximately 360 days, remember they probably couldn't measure like position of the stars that accurately that long ago. But maybe they were like, hey, I noticed that every 360 days, our planet gets kind of back in the same position. And it's a cycle. It's a circle. 360 days approximately in a year back then when it was lower accuracy. Do you think that could be a possibility?
Yes.
I think so. I think it makes sense. I don't know for sure. I wasn't alive back then. But that seems to be kind of the reason. And because of that, we've been using this 360 degree measuring system for the amount of rotation or for angles. But it doesn't really work that great mathematically. It's not a precise number. It's not based off of like a property of the circle. So instead, in more recent years, mathematicians and scientists, dudes, were like, hey, let's make up a brand new way to measure a circle, something that's based off of the property of the circle itself. And they all agreed that, well, the one defining characteristic of every circle is its radius. The size of a circle is dependent entirely upon its radius. Just like the circumference or the area, everything about a circle is based on its radius. So they said, what if we measure the amount of rotation, or the degrees, so to speak, around the circle in terms of the radius? Like how much of the radius around the circle are you? So imagine this. Imagine if you took that radius and you measured it. Maybe that's like 6 inches or something, or 5 inches. And what if you then walked around the circle that distance? So you might get about that far, right? Do you see my purple line there? Like that's roughly the length of one radius. If that were 5 inches of a radius, if I walked 5 inches, I would get about that far around my circle. And so then they could say, well, I could measure that. I could figure out what that angle is. And then they thought, all right, well, how many radii, would it take for me to get all the way around the entire circle? And so then they counted. It was like 1 radius, 2 radius, 3 radius, 4 radius, 5 radius, 6 radiuses, and then a little piece of a last one. And guess how many radiuses it took to get around the circle? It's not exact. It's a decimal, but it's approximately 6.28 radiuses.
You are so smart, man.
This is 2 times 3.14. Or more accurately, this is exactly 2 pi. What? So they learned that it is exactly 2 pi radiuses around a circle. And even if you have a smaller circle, it's got a smaller radius, doesn't it? So a smaller circle has a smaller radius, but that distance around is still even if it were a smaller circle, since it has a smaller radius, it's still exactly 2 pi radiuses all the way around that circle. And so then they decided, hey, let's use this new unit called a radian to represent the radius of the circle. Now, pi in itself, this is an irrational number. It goes on forever. And that isn't a number they just pulled out of thin air. That number they discovered by taking let's see. So if you compare it's a ratio of the circumference of a circle. Remember how the circumference is the distance around it to its diameter? if you take the circumference of any circle and you divide it by its diameter, you're always going to get exactly pi. So that's where pi comes from. It wasn't a number that they made up. They didn't just say, hey, let's make 3.1415926589739 into this magical math number that just works out. Instead, they learned that if you take any circle, no matter how big or how small it is, and if you measure the circumference, the distance around the circle, and you divide that number by the distance across the middle of the circle, it'll equal 3.1415, blah, blah, blah. And then it also turned out that if you take the radius of that circle and you wrap it around the edge of the circle, it turns out that one complete rotation around that circle is 2 pi radiuses, or 2 pi radians. So that's where the word radian comes from and what that measurement represents. So this is a much more precise unit of measurement as opposed to that somewhat arbitrary degree, right? The length of a degree, that was just some number that people picked out of thin air for the most part. But a radian, this is a precise unit of measurement based on the property of the circle itself. 1 radian is equal to 1 radius of that circle. And then it turns out that the distance all the way around the edge of the circle is exactly 2 pi radians, which is kind of nifty because if you remember the formula for the circumference of a circle, see? It equals 2 pi r. What does r represent in that formula? The radius. It's 2 pi radiuses, or 2 pi radians, if you want to think of it that way. Their circumference is exactly 2 pi radians, or radiuses. Isn't that crazy?
Yeah.
Come on, kind of neat, right? I like it. And think about how it applies to this unit circle or to the coordinate plane. So here's what we got. A full circle, one time around, one full revolution or rotation, is exactly 360 degrees. Well, that's what we call 2 pi. So I've got another little coordinate plane here. This starting point is 0 degrees. It's also 0 radians. Now, when we went all the way around that circle, one full rotation, we got 360 degrees. But in terms of radians, one complete time around that circle is exactly 2 pi radians instead of 360. What I want you to do is try to think about what would those other 3 angles be in terms of radians or in terms of pi, essentially. And you can think about like fractions or whatever. You can use my hints up there above it. I would start with figuring out what 180 degrees would be. All right, so we'll start with the obvious one. Most of you seem to have got on to that, which is great. And if all the way around the circle, if one complete trip all the way around is 2 pi radians, then what would half of that trip be? Well, what's half of 2 pi? Just 1 pi, or just pi. So we would say that on the negative x-axis, or over to the left, this measurement right here, where we would have like 180 degrees, that's equivalent to just pi radians. It's half of 360, or half of 2 pi. So on the far left, that's going to be pi, because all the way around it is 2 pi. So every like half of a circle or half of a rotation around that coordinate plane is another pi. All right, now what about up top at 90 degrees? What would this value be? Anyone have a hypothesis or an educated guess, perhaps?
1
How much? 1.5? Or a half? Aiden, what do you think?
Half pi.
Why do you think it's half of a pi? Yeah. If all the way over to here, shoop, is a whole pi, well, if I cut that in half, when I have literally like half of a pi, and so the way we'd write this, instead of writing like 1/2 of a pi, is you're going to see that written as just pi over 2. It's literally pi divided by 2. So straight up, the positive y-axis, 90 degrees, is actually pi over 2 radians. Now the last one that you have to think about, down at the bottom, how many radians would that be? That would be the 270 in degrees. Anyone figure out what that one would be? 1.5 of a pi. Because if we think about it, if 1 quadrant is half of a pi, if I want another one, I've got 2 halves of a pi. Well, 2 halves makes 1 whole pi. And if I go one more quadrant, hey, how many halves of a pi did I get? We'll count them up, 3, right? 3 different quadrants, each one of those is half of a pi. Then by the time I get down to 270, I have 1.5 pies, or we write that as 3 halves of a pi. And we're going to write this as 3 pi over 2, which is the same thing as 3 halves of pi. And again, that is 1.5 pies. We'd write it as the improper fraction 3 pi over 2. Anybody notice anything on this magical graph over here yet? Take a look at the top, pi over 2. Over there's pi, down at the bottom, 3 pi over 2. Ooh. Can't wait to learn about that later this week. It's going to be so much fun. So those are your different key radian values. Now, the one thing that was common that we can use to easily switch between them. So right now, this is all brand new to you. And so you're going to probably need to spend some time, or if you do forget what these values are, if you can't think it through, a nice thing you can do is you can always just convert the angle in degrees, which you're more familiar with, into radians by a very simple conversion factor. Knowing that this 180 degree mark on the left is also pi radians, we can use that knowledge to help us convert between the two different measurements. And so this is called a scale factor. When you're converting from like one unit to another, you multiply it by a scale factor. You know, like 12 inches are in 1 foot, so 3 feet, you multiply that by 12 and you get, oh, there are 36 inches in 3 feet. So to convert between radians and degrees, now by the way, this is the actual learning target 9.2, all right? So this is what you're just going to be tested on Friday. And this is a bit simpler, but we need to conceptualize the rest of those parts to get to this point, to understand where these angles are coming from and how they're related. So to convert between radians and degrees, we just multiply by this, one of these two fractions, either 180 degrees over pi or pi over 180 degrees. Now, normally, whenever I convert something or I change its, or I multiply like a fraction by something on the top and bottom, we normally have to multiply by the exact same quantity, like 5 on the top, 5 on the bottom, which we're allowed to do because 5 over 5 is equal to 1, or 12 over 12, or whatever. Like normally when we get a common denominator, you know, how you multiply the top and bottom by something. In this case, though, if I wanted to convert 60 degrees into radians, like how many pi radians is that? Well, then I would multiply by pi over 180 degrees. Now, at first glance, that seems like an illegal math move. I can't multiply by one value up top and a completely different value on the bottom, right? Pi and 180 degrees, those look like very different values. But are they? Is pi different from 180 degrees? It's the exact same thing. So all I'm really doing here, I'm multiplying by 1 because pi and 180 degrees are the exact same thing. So we are legally allowed to multiply by this. Now, by putting the 180 degrees on the bottom, I've got degrees on top, degrees on bottom. They will cancel out. That's what we want. If I have degrees, I want the degrees to cancel, and I want to be left with the pi radians. If you want, you can write this 60 degrees over 1. I know that sometimes helps you with fractions. Then for multiplying, you just multiply across the top and multiply across the bottom. 60 times pi is 60 pi. 1 times 180 is 180. Notice there's no more degree symbol. The degree units canceled out and we're left with these pi radians. Now we also want to simplify the fraction if we can. So for this one, what I do is I notice that they both have a 0 in the ones position, so I could divide both of those by 10, essentially just crossing off the zeros. I'm left with 6 over 18. Can I simplify 6 over 18 further? For sure. Those are both divisible by 6. And if I divide both those numbers by 6, I'm going to get just a pi up top, or 1 pi up top, and I'm going to get a 3 in the denominator. And so 60 degrees is the same as pi over 3, or 1/3 of pi. If you even look at one of these fancy graphs here, pi over 3, that's 60 degrees. And if you think about like slicing it here, this would be like 1/3 of pi, that'd be 2/3 of pi, and this would be a whole pi. It's like if I split the pi up into thirds, that'd be one of them. And we'll look at that more later on this week, on Friday. Now for 3 pi over 4, that's now doing the opposite. I've got my units in radians, because there's a pi in there, and I want it in degrees. So we have to convert it. So we're going to multiply by our conversion factor. But we need to think, wait, is it going to be 180 degrees on top and pi on the bottom, or the reverse? And to make sure you know which way you're plugging them in, is always look at which unit you have, which unit you're given, and put that same unit in the denominator of your conversion factor. So since this has pi in the numerator, I want to make sure that the conversion factor has pi on the bottom in the denominator, so that it cancels out, which will leave me with degrees up in the numerator. So I'm going to multiply by 180 degrees over pi, and now the pi's will cancel out. We don't need to actually multiply them through, being converted. Multiply across the top. Well, 3 times 180 degrees is 540 degrees. In the denominator, I just have a 4. And that's just a simple division problem. 540 divided by 4. What's that going to give us? That's right. 135 degrees. You what? Yes, you're going to have questions just like these two on your test on Friday. Pretty easy, right? Of course. All right, go ahead and try the next slide. I want you to try to convert these two on your own. So convert the degrees into radians, and then convert the radians into degrees. Mm-hmm. Good. Nice. Mm-hmm. Yes. I do love, there's been more than a few students who I've seen with just circles on their notes in the margins, trying to draw the perfect circle. Awesome. Yeah. Cool. Yeah, it has. Looks good. Getting them? Yeah, that's it. All right, I like what I see. Can I do the first one? Okay. So since it's given to me in degrees, I want the degrees to cancel out. So I'm going to make sure that 180 degrees is in the denominator. So I have degrees on top and degrees on bottom. They'll cancel. That means I need to put a pi in the numerator to get radians. Cross off the degrees. That leaves me with 45 pi over 180. If you simplify that fraction, you should get pi over 4 radians. That's 45 degrees. For the second one, I see pi in the number already, so it is in radians, and I want that to cancel out. So I'm going to put a pi in the denominator so that I have pi on top, pi in the bottom, which means I'm going to put the 180 degrees up in the numerator. When I multiply these, I'm going to first cross off the pi's. They're going to cancel, one up top, one at the bottom. Negative 3 times 180 is negative 540 degrees divided by 5 in the denominator. And when we divide that out, we get negative 108 degrees. Anybody else get those two values? Yes! Oh, that's wonderful news. Very cool. So that's converting between radians and degrees. And that is actually learning target 9.2, which you will be assessed on. Give me a thumbs up if you think you can handle this on the test on Friday. Yeah, pretty good. Remember, the only other new target then will be the law of sines and law of cosines. So make sure you look over some of those problems this week. You all were doing awesome with it last week, like on those practice worksheets. You did really, really well on those. Yeah. The one older target is 8.3, which is graphing the rational function. So identifying the asymptotes, the holes, the intercepts, and then graphing those like double swoopy curve type of things. So that's going to be the only recessed one. The test should only take you like half an hour. It's not going to be a whole class thing, just part of the class. And then we do have then more lesson to go through. All right, almost done. Almost done. This looks familiar, right? We had like these exact same diagrams earlier, but those were in degrees. Guess what we need to do now? Find these angles in radians. Now you could convert these into degrees, find what the angle was, and then convert that final angle back into radians, but I want you to practice using them in radians, right? That's the whole purpose of this. It's a new unit. Now I'll do this with you, don't worry. So this first one, if you recall when we were in degrees, this was like an additional 70 degrees on top of the 90. Whereas this vertical one was 90 degrees and I went 70 degrees past it. And we added those two numbers together. But these are in radians, so I need to think about what are these angle measures in radians. Up at the top here, at the positive y-axis, do you remember how many radians that was? Half of a pi. Good, very good. So we'd write that as pi over 2. So if I rotate this first quadrant, like each quadrant is pi over 2 radians. So I'm going to start with pi over 2 radians, and then from that pi over 2 mark, I'm going to go an additional 4 pi over 5 radians. So I'm going to add those two values together, and that'll be my total angle in radians. So we just kind of write out a little math problem. and say, okay, I'm starting with pi over 2. That was the first rotation, plus an extra 4 pi over 5 radians. And we just add those numbers together. And that's going to be our terminal angle in radians. I've got 2 fractions. Hey, what do we need to do to add fractions together? Oh, it's exactly right. We need a common denominator. Look at 2 and 5. What is the LCM of 2 and 5? 10. Let's make those both into 10s. You could do 1,000 also if you really wanted. I'm going to multiply this by 5 over 5. Right, I can multiply by the same thing on the top and bottom because that's equal to 1. This one I'm going to multiply by 2 over 2. Rewrite these fractions with the same denominator. And we have 5 pi over 10 plus 8 pi over 10. Now that they have a common denominator, they're both going to be, or this sum's going to be over 10. But now I'll just add the numerators together. Well, 5 pi plus 8 pi gives me a total of 13 pi over 10. You didn't steal your answer. It's just the correct answer. I don't... Maybe you both got it right. Could it be that? Could you both be proud of your own individual successes? Or do you base your own value and self-worth entirely off of the other person's accomplishments? It's a tough way to live. Anyways, this middle one, everybody, this pi over 3 measurement, do you guys remember how many radians it is on the negative y-axis? How much? 3 pi over 2. That's correct. So that's 3 pi over 2. But this measurement that's given to us, that pi over 3, that's going backwards. That's in the negative direction. And so I'm not going to add that to my 3 pi over 2. I'm going to subtract it. So let's subtract pi over 3. Because we're going backwards. All right, now I've got 2 different denominators. What's the LCM of 2 and 3? 6. Let's make those both 6's on the bottom. I'll multiply left e by 3 over 3. I'll multiply right e by 2 over 2. It's going to give us 9 pi over 6 minus 2 pi over 6. So both fractions are over 6 at this point. What's 9 minus 2?
6.
Wow, that's awkward. 7. 7 pi over 2. 7 pi over 6, excuse me. Okay, this last one's actually the easiest of these 3. Okay, you ready, everybody? I'm starting here. 1 complete time around the circle. How many pi's is that? That's 2 pi, right? 1 full rotation is 2 pi. I'm going another full rotation, which is 2 more pi. But wait, JD, then after I added those 2 more, this is only half that way, plus just 1 more pi. You add those up, and you just get 5 pi, right? So each complete rotation is 2 pi, but then that last half a rotation is only 1 pi, because that's half of 2. Oh no, I'm sorry that my pi's look like 11s with an accent. But I don't really know why I'd draw an 11 with an accent over it. Did you... what's your preferred pi? Would it be just like a flat top?
No,
You want it? It's got to be curly, but it's got to like hit it like that. What? You want like that? It's do I have to have the curve? But it's like this one's taller and this one's lower. Okay, what about this? Mmm. There's your pie. What? That's not pi, that's mu. That's mu. Yeah, mu. Not the Pokemon character, but the Greek letter mu. That's the Greek letter mu. This is the Greek letter pi. That's the Greek letter theta. That's the Greek letter phi. These are all Greek letters. That's alpha. Omega. Sigma. Any physics flashbacks, anybody right now? Love theta. Okay, everybody. In the back, can you try this last slide for me? Coterminal angles. Not 360, but you could convert them all to degrees and then add or subtract 360. But if we didn't want to convert, if we wanted to stick with radians, how much should I add or subtract from each of these angles to keep it in radians? She stole your answer, man.
I still have a question.
Yeah, what's up?
So we were wondering back here, were you in a frat in college?
No, I was not.
Why did you leave? I don't remember it at all.
But I was in a club. I was actually the president of the Miami University Inline Speed Skating Club. Yeah.
I don't know how to ice.
Yeah, you know, like racing, but with inline skates, not ice skates. But same idea, you're racing around a rink. Yes, Miami University, though, which is actually in Ohio, not the University of Miami. That's the Florida one. No, it's a great school. I mean, my Miami was actually a university when Florida still belonged to Spain. So we are the real Miami. Just saying. All right, so for all of these, all we're going to do is add or subtract 2 pi instead of 360. So like to get a coterminal angle to 7 pi over 8, we had add 2 pi. I'm just going to do one of these with you because that's, I think, enough for you to get the idea. So that's 2 pi over 1, but to add 2 fractions, what do we need, everybody? Yeah, let's make that common denominator of 8 by multiplying by 8 over 8. And so we're really going to be taking 7 pi over 8 plus 16 pi over 8. And if you think about it, isn't 16 pi over 8, isn't that the same as 2 pi, right? 16 divided by 8 is 2. But with that common denominator, I can keep that 8 in the bottom, and I'm just adding the numerators. And 7 plus 16 is 23. No, you're not. You're a 23-year-old in Algebra 2? All right, for a negative coterminal angle, we know we need to get the common denominator of 8 again. It's just going to be subtraction. So I'm just actually going to use this same exact fraction, but I'm going to subtract the 16 pi over 8. Because remember, that 16 pi over 8, that is that full circle, that full cycle of 2 pi just written with a common denominator. And this is going to be over 8. 7 minus 16 gives us negative 9 pi over 8. So that's one positive coterminal angle and one negative coterminal angle. For the middle one, the negative pi over 2, same idea. You just need to get a common denominator Oh, when you're adding or subtracting 2 pi, you just need to get a common denominator of 2. All right, the last one is actually pretty easy because it's not a fraction. So if that's 10 pi, what's a coterminal angle to 10 pi? Yeah, it's 12 pi. You just add 12 pi. What's a negative coterminal angle to 10 pi? There it is. Keep on subtracting 2 pi's. Eventually you'll get to negative 2 pi or negative 4 pi. You're just subtracting 2 pi over and over again. All right, that's pretty much it. That's quite the lesson today, wasn't it?
Amazing.
Hey, I have a great idea, everybody. Should we take a look at the homework? Yes.